Welcome to the fourth lecture of Principles of Vibration Control. In this lecture, we will do a bit of board work, because I will try to show you first of all the viscous damping model and how the energy is dissipated through a viscous damping model, and then we will take up a very simple case in which we will see that for a single degree of freedom system, how actually we can get the governing equation of motion and how we can predict that which part of this frequency domain transfer function of the system is actually stiffness dominated or damping dominated or dominated by the mass of the system. So, phase by phase we will go through that, but to begin with first we will do the first viscous damping model of a system. So, when we talk about viscous damping model, here we are talking about the damping force which can be modeled in terms of a piston and a cylinder, and the cylinder whenever you are trying to give a driving force to the cylinder, you are going to get a resistance inside the viscous fluid, and this viscous force will be proportional to the velocity. So, if this fellow moves at a speed x, at a displacement is x and the velocity is x dot. So, the damping force is modeled as it is proportional to the velocity of the system, and hence F d equals to C x dot, and this is the conventional representation of the system. Now, let us say that this is happening in a manner to and fro. Okay. So, that means this system is going back and forth, okay, and we want to find out that what is the energy that is dissipated in one cycle. So, x in that case can be represented by a periodic signal. So, we can write it as something like x equals to a sin omega t. So, that it is periodic. That means, if I try to visualize x with respect to time t, x versus t, then it will come something like this, where a is the amplitude. Now, that is what is my displacement, the periodic displacement that I am giving to the piston, and I am trying to find out that what is the viscoelastic energy dissipation per cycle. So, x dot will be a omega cos omega t, and let us say the force is C a omega cos omega t, and the energy that is dissipated per cycle, if we try to find that out, that means for a time period of 0 to t, where this t is 2 pi by omega. Okay. So, we will do that, and the total energy that is dissipated in the system can be written in terms of F d, that is the driving force, and that times x dot dt. In other words, this will become integration of 0 to 2 pi by omega, and this will become C s square omega square cos square omega t. So, that is that is the energy that is dissipated per cycle in the system. Now, let us try to evaluate this. It is a very simple integration. Let us try to do that. That means, what we have to find out is what is this 0 to 2 pi over omega and c omega square cos square omega t, where c is our damping coefficient, a is of course the amplitude, that is a constant. So, we can write it in terms of c, and let us say we divide it by 2. So, we get 0 to 2 pi by omega. So, omega square also we can take it out. Okay. So, then what we are getting is 2 cos square omega t dt. Now, you already know that cos 2 omega t is cos square omega t minus sin square omega t, which means it will be 2 cos square omega t is 1 minus cos square. So, minus 1. In other words, our 2 cos square omega t can be simplified as 1 plus cos 2 omega t. So, we can write this here as c omega square by 2 and integration 0 to 2 pi by omega 1 plus cos 2 omega t dt, which means this will be c omega square by 2 and then t plus sin 2 omega t divided by 2 omega 0 to 2 pi by omega. If we further go ahead, then we will see that this will become only the sine terms are going to get cancelled, because sine 4 pi will be 0. So, and sine 0 is also 0. So, this will become c omega square times 2 pi by 2 omega, 2 are cancelling. So, we are going to have only pi c omega with us. So, if that be the thing, we can borrow this part here, so that we can now write down that this is essentially the amplitude of the system and pi c omega a square. Okay. So, that is the energy dissipated per cycle. So, we can see from this expression that d, the energy dissipated per cycle, varies with square of the amplitude. So, if the amplitude is very high, energy dissipation will be very high. It also varies with the damping coefficient c. So, for larger damping coefficient, energy dissipation will be more, and it also varies with omega. So, that is what this expression is going to give us, that how the energy is dissipated from a viscous damping model. Now, we can also visualize these in terms of kind of a geometric interpretation of the system. In order to do that, we will simply need to plot this viscoelastic damping force. So, if we do that, then this will become, we have to consider that how these force versus deflection relationship will come into picture. So, we already know that F d over C a omega equals to cos omega t. That is one relationship we know, and also we know that the normalized displacement x over a is sin omega t. So, this essentially tells us that x over a square plus f d over c a omega square equals to unity. This gives us the clue that we can actually represent this whole viscous energy damping in terms of the work done in the system. So, that means if we plot f d over x, this will take the form of an ellipse. So, this will be like an ellipse such that the semi measure of the ellipse is the amplitude A, and the other direction, this is C A omega, and the area under the curve is essentially the energy that is dissipated per cycle in a viscoelastic material, in a viscous damping material. Now, if it is a viscoelastic damping system, then this is going to change slightly. What will happen is that in that case there is something more in case of viscoelastic damping. So, if instead of viscous damping, if it is viscoelastic damping, in that case what you have is not just a simple damper, but a combination of a spring and a damper. There can be various combinations possible. This is a combination in which the spring and the damper are in parallel, and this combination is known as kelvin-voight model. Now, if I use this combination, then this diagram will slightly change. The energy dissipation will now take care of this dissipation as well as the spring factor in a way that the orientation of the ellipse will depend on the spring stiffness, and instead of the f t versus x relationship, in this manner it will become an inclined ellipse system. So, that is what is the viscoelastic damping model. Now, what we are going to find out is actually that how, in terms of this model, we now know that what is the energy dissipation and what is the kind of a geometric interpretation of the system. But going further, we would like to integrate this system with the a single degree of freedom system. Let us first start with a single degree of freedom system, and let us try to prove one of the concepts that we have already discussed, that for a single degree of freedom system, what are the parameters that affect the vibration control at various points of time. To do that, let us first draw a single degree of freedom system. So, let us say this is our boundary, and we have a single degree of freedom system which has a Kelvin-Voight model type of a damping, and the spring and the damper is attached to a mass in this case, and the mass is resting on a frictionless wheel. So, these wheels are frictionless. And let us say that we have applied an excitation force F, which is harmonic in nature. Maybe we can represent it as F bar e raised to the power j omega t. And let us say we are tracking with the help of a sensor the displacement of this mass m when we are subjecting this system to this harmonic excitation, and let us say that this displacement is x t. Now, presumably if I give this harmonic excitation to the system x t, the response will also be harmonic, and that we can write in terms of x e raised to the power j omega t. Our intention now will be first of all to get the governing equation of motion of such a system, and then to show that how we can predict about the nature of the response and how various parameters will be affecting the nature of the response. So, first of all let us try to get the governing equation, which we can do very easily by applying Newton's law. So, if we draw the free body diagram of the mass m, then one of the force that is working is F, which is F bar e raised to the power j omega t, and we have this harmonic force is getting resisted by the spring, and the spring force is proportional to the displacement. So, it is k x, and also by the damping force is proportional to the viscous damping here. So, to the velocity of the system, that is what we have just now discussed. Now, in addition to that, for dynamic equilibrium there has to be an inertia force in the system. So, since the displacement is in the right side, so this inertia force we will be showing it as a pseudo force, D'Alembert's force, and that we will be writing as mx double dot. So, these are all the forces that are working on this system. Now, I can sum up all the forces, that means all the forces in the left hand side together, that is k x plus c x dot plus m x double dot equals to all the forces in the right hand side, that is the force acting on the system, that is F bar e to the power j omega t. So, with the help of the force equilibrium along the direction x, it is a unidirectional motion, we are going to get the governing equation of motion of the system. That is the governing equation of motion. In this course, many a times we have to derive such governing equations of motion. Now, we can try to find out that what will be the solution of this system, not in the transient case, but in the steady state. Okay? That means, after some kind of a finite time, what will be the nature of solution of the system. So, in the steady state, the response is also harmonic in nature. So, this is the steady state response of the system, and if I substitute this steady state response, then what I am going to get is k x e raised to the power j omega t plus c j omega x e raised to the power j omega t minus omega square m x e raised to the power j omega t equals to f bar e raised to the power j omega t. Now, since t not equal to 0, so e raised to the power j omega t not equals to 0, any steady state time after t equals to 0 you are considering. So, t not equals to 0, e j raised to the power omega t not equals to 0. As a result, you can cancel these from both the sides, and you can get this as the steady state response of the system as k x plus j c omega x minus omega square m x equals to f bar. If I slightly reorganize this, I am going to get the steady state response of the system as k plus j c omega minus omega square m times x equals to f bar. That is the steady state response of the system. Now, we can further try to see the steady state response in terms of as we change the excitation frequency. So, let us try to do that. So, now what we can say is that x equals to f bar over k plus j c omega minus omega square m. And if I work on this, I can also write this as, if I divide the numerator and denominator by k, then it would become 1 plus j c omega by k minus omega square m by k. I have a purpose in terms of dividing the numerator and denominator by k. The purpose is that f bar by k is nothing but the static deflection of the system. So, we can also write it as delta static deflection of the system, and the rest of the thing we can write it as 1 plus j c omega by k minus omega square m by k. We can now try to further simplify this whole thing. In order to do that, we have to keep a few basics in our mind. So, let us try to work out these few basics here, and then we will attempt to write this expression in a manner by which we can actually get the nature of the response easier for us to understand. In order to do that, we have to keep first of all in our mind that there are two things that is there. One is called a non-dimensional excitation frequency we will use, which is also a kind of a normalized excitation frequency, and that we will define as capital omega, which will be excitation frequency divided by the natural frequency of the system omega n, and that means it will be omega divided by square root of k over m for a single degree of freedom system. We know that omega n equals to square root of k by m for a single degree of freedom system. Also, we have to think of the damping coefficient, and there we would like to introduce a new term called damping ratio zeta, which is once again the damping normalized as C divided by Cc, where Cc is known as the critical damping. Now, I would not go into the basics of it. You can check the details of it from any basic textbook on mechanical vibration, which is the prerequisite of this course, Thompson's book, let us say, and you can see these derivations. So, Cc is actually derived as square 2 times square root of Km. That is what is the definition of the Cc. So, we need to find out that what will be the C omega by k term. So, we can try to find it out, and also the other term is then already there with us. So, if we try to find that out from based on this expression, that we can write that C omega by k is what we are planning to find out, and this C omega by k we can write it in terms of the damping ratio of the system, integrate that. That means we can express the C as 2 zeta root k m, and that is what is our the expression of C, as you can see here, that it is 2 zeta root k m. So, this times omega divided by the k. In other words, this can be written as 2 zeta root m by k times omega. Okay? This is a multiplication simply. Please do not confuse it with the the steady state amplitude of the system. So, it is 2 zeta root m by k omega. In fact, we can write it further in terms of the non-dimensional frequency then, that it is 2 zeta omega divided by square root of k by m. That means it is nothing but 2 zeta capital omega. So, this is the relationship that we will like to borrow here, and then we are going to get a better simplified normalized relationship. So, let us try to write that steady state normalized relationship, which will be useful for us in order to predict the response of the system. And now we can write that the steady state response x is nothing but delta static over 1 plus j c omega by k. We have already derived that c omega by k is 2 zeta omega. Okay? That is what we have already derived. So, it is j 2 zeta omega minus this part, of course, you can very easily do the same way, that omega square m by k is nothing but omega square by k by m. That means omega square by omega n square, that means it is capital omega square. So, minus omega square. So, that means I can write that x equals to delta static over 1 minus omega square, that is one part, plus j 2 zeta omega. Now, that is the response that we are getting from the system. Now, let us say that we want to find out the amplitude of the system. So, if I am interested, because this is having a complex, as you can see the response is complex. So, if we want to find out the amplitude of it, then it will become the amplitude of delta static divided by 1 minus omega square whole square plus 4 zeta square omega square square root of the whole thing. That is the because it is the ratio of the numerator amplitude of the numerator and the denominator, and the denominator is a complex quantity. So, we have to find out the amplitude of it, which we have done in this manner. Now, we have everything that we require in front of us. All we have to do now is that for certain conditions, we have to find out what are these conditions we are talking about. The conditions we are talking about are just 3 conditions right now. One is when omega, the excitation frequency ratio, is very much less than unity, which means this omega is actually very small in comparison to omega natural frequency of the system. So, that is your capital omega to be very less than unity, and then omega is approximately unity, and then omega is much greater than unity. Now, let us try to see as an engineer what will be approximately the response of the system under these 3 conditions. Okay. This is our case A, this is case B, and this is case C. So, if you look at case A, in that case x will be approximately, you can see that omega is very small. So, that means I can neglect this, it will be very small, omega to the power 4 also will be very small, and omega square also will be very small. So, x will be approximately what? it will be the amplitude of f over k. That is what is our f bar over k. That is what is our first case. So, in this case we can write that x is approximately amplitude of f bar over k, which means my response is stiffness dominated when the omega is very, very small. Second case, omega equals to 1, omega equals to 1. If I substitute, then what will happen is that this term will become 0 and this term will become after square root 2 zeta omega. So, in the second case x is f over 2 zeta omega k. Now, let us try to find out what is this zeta omega k. We already know all the definitions here. So, we can try to apply all these things here and try to find out that what is this 2 zeta omega k, what does it means for us in terms of the damping constants and the all other properties of the system. So, 2 zeta omega k would mean 2 c over 2 root k m, that is what is our c c, then omega over omega n, that is square root of k by m, and then multiplied by k. So, this 2 and 2 will cancel and the square root of k will cancel with k, and the square root of m will cancel, and we are going to get only omega c. So, what it means is that this expression is actually nothing but f bar over omega c or c omega. So, that means here x approximately equals to f bar over c omega. So, that means at this region when omega is approximately equal to unity, this region the vibration response is actually damping dominated. Let us now go to the last part, that means when omega is much greater than unity. What are we going to find in such a case? Well, when omega is much greater than unity, let us try to see that what is going to happen to the expressions. So, if we erase all other things, we have the basic expressions with us, okay, and here also we have it as 4 zeta square omega square. That was our basic expression, and here now omega is much greater than unity. That would mean that in this denominator the highest term is actually omega square square. That is the only term that will be much larger in comparison to any other term. So, what it will mean is that for such a case x will be approximately f over k times our omega square itself, and that means it will be approximately f over k times omega is our as you can see here that this is the expression of omega. So, we can write from here that omega square is nothing but omega m omega square over k. We can derive it by looking at this expression itself. So, this can be written as k times m omega square over k, this k and this k cancels. So, the approximate expression is f over omega square m, that is the approximate expression. So, in this case x is approximately let us put it as f bar, which I am missing. So, f bar. So, it is f bar over omega square m. This is also interesting. So, that means in a particular region vibration control has nothing to do with damping, but to do with the mass of the system. When the omega is much greater than omega n, this omega when it is much greater than omega n, in that case it is all the mass that matters. So, this is mass dominated. So, thus if I try to sum up this total result in terms of the transfer function representation of the system, and then what we are going to see is that this clearly tells us that there are 3 regions here. If I plot this omega with respect to the transfer function of the system, we are going to see that these representations will take up the form like this, in which there is a part up to which this excitation frequency omega can be considered to be much less than unity. This is the peak point where omega is unity. So, this part is actually stiffness dominated. Then in between there is a part which is actually C dominated, damping dominated, and when omega is much greater than unity, then you are going to get the part which is actually mass dominated. So, the important take home message for us is that is why the characterization of the system is important. If the excitation frequency of the system is low in comparison to the the resonance or the first natural frequency of the system, we should not look into C or mass as the parameter. C or mass would not be important, only K will be important, because it is stiffness dominated. If I come here close to the resonance, we should not look into stiffness or mass, it is only the damping constant which will be important. If we come to the right hand side where it is the excitation frequency is much greater than unity, then the entire response of the system will be dominated by the mass only, nothing else will have impact on the system. So, that we can prove it with the help of all these basic definitions of the system. Thank you.